Ladies and gentlemen, dear colleagues, dear Ondrej, Director Schneider, on behalf of the Austrian Academy of Sciences, I want to welcome you to the second Richard Zsigmondy Lecture, which is jointly organized by the Austrian Academy of Sciences and the TU Wien since 2021. The Zsigmondy Lecture is within the framework of the Academy Lectures. So in these Academy Lectures, the Academy invites really top-class scientists internationally from all disciplines, and the goal is to inspire the interested public and make it aware of the wonderful science that's done worldwide and also of the societal challenges. So for example, end of the month, there's one, the Gerda Schwarz lecture that will take place also at the Academy on the 28th of November, and Timothy Potts, he's the director of the Getty Museum in Los Angeles, will present this museum. So it's really across all disciplines, which is a hallmark of the Austrian Academy of Sciences. Today we focus on pioneering achievements in microscopy, and that's what this Zsigmondy lecture is named after. So the Nobel Prize winner Richard Zsigmondy was an Austrian-Hungarian chemist and researcher in the field of colloid chemistry and microscopy. The Austrian Academy of Sciences is old enough that we can claim also people who were part of the Austrian-Hungarian Empire. He received the Nobel Prize in 1925 because he developed an ultramicroscope, a special version of a dark field microscope, where already in 1912 they could see 4 nanometer sized particles by looking at the light scattering. As I mentioned, in 2021, the Zsigmondy Lecture was inaugurated at TU Wien, and the first speaker was Stefan Hell, also Nobel laureate, also did super high resolution microscopy. But today, we're very honored to have Ondrej as our next prominent speaker in the series, and Jens will take over introducing him. Thank you.
Thank you very much, Ulrike, for that introduction. And first of all, before I go to your CV, Ondrej, I would like to thank you that you came over all the way from the US to honor us with this lecture today, because I think this topic is very interesting, especially as it comes to new technology and the science comes together. Ondrej Krivanek is a physicist of Czech and British nationality, now resident in the United States. He was born in Prague, so in the former Austrian-Hungarian Empire somehow. He moved to the UK in the late 60s and first obtained a degree from the University of Leeds. Then he moved to Cambridge and worked on a PhD with electron microscopy also already at that time. After Cambridge, he had postdoc positions in Kyoto in Japan and at Bell Labs, and I just learned last week that Bell Labs was really an important source of excellent researchers throughout the world. Obviously, this is true, and you're one of them. And also at University of California in Berkeley. During this time in Berkeley, he became interested in electron energy loss spectroscopy and built his own spectrometer. So it's not just a theory, but it's also the practice that you bring together. And this is also interesting because then later at the NSF, at a facility at Arizona State University in the 1980s, you started collaborating with a company, first as a consultant, and then you moved permanently to the company somehow. Today, I think that could be also called startup stuff in a certain context. He then went in 1995 back to Cambridge, and he worked on aberration correction of electron lenses, and then he also started Nion Corporation in 1997, a company you're still president. So you also always try to merge science and practical application in a company. With Nicholas Delby and IBM's Phil Batson, he obtained sub-angstrom resolution. Sub-angstrom, for me as a civil engineer, I cannot really grasp that you can go really to sub-angstrom resolution with a scanning transmission electron microscope The first results published in 2002, so about 20 years ago now. And you're one of the major experts in electron microscopy and electron energy loss spectroscopy. You won the Kavli Prize for Nanoscience in 2020 for your substantial innovations in atomic resolution, electron microscopy, and then there's a couple of medals. I don't want to call them all, but I think it's impressive that you also got the Duddell Medal, the prize of the British Institute of Physics, and the Cosslett Medal from the International Federation of Microscopy Societies. You're a fellow of the Royal Society, the Institute of Physics, the Microscopy Society of America, and of the American Physical Society, and honorary fellow of the Royal Microscopical Society. So a couple of things you also do, and thank you very much for having you here today. We are curious about your lecture, and yeah, thanks to prepare it for TU Wien and ÖAW together. Thank you.
So thank you very much. It's a pleasure to be here. As was mentioned in the introduction, there are certain links from centuries ago, Austria-Hungary. My mom studied in Vienna, and my grandpa did an apprenticeship here that taught him how to build motorcycles. And he did a good job. He has a motorcycle in the Czech Technical Museum now in Prague. So it's a pleasure to be back here, and I thank the Austrian Academy for the invitation. And we have about, I guess, 50 minutes for the talk, 10 minutes for questions. So let's move on. So my opening slide, nothing to do with microscopy, more with perspective on life. There's a beautiful mountain here in northern Washington state, so the northwest corner of United States, close to Vancouver in Canada. And to get to this point, you have to kayak along this lake. There's no motorized transport or anything, so private initiative campsites along the lake. It takes about 2 days to get down here to the bottom. Then you have to climb a mountain almost 2,000 meters, starting at not much above the sea level. And when you get to the top, there's a fire lookout. So we have a lot of forest in Washington state, as you can see. And people were worried about fires. Nowadays, you have helicopters and planes and satellite reconnaissance. Back in the 30s and 40s, we had huts up on the tops of mountains. And some of them are still manned. So there's actually, right behind us, right behind the slide, there's a little hut that a person lives the whole summer in. And they get supplies dropped off by helicopter every now and then. And the hut is kind of famous. Back in the 60s, a poet by the name of Jack Kerouac spent the summer there composing poetry. So this is the context, Desolation Peak. You can buy a book from Amazon, Jack Kerouac on Desolation Peak. So it's well worth the effort. And when you get to the top, you get a beautiful perspective over the mountains of northern Washington. And if you turn around, then you're looking up into Canada. You're about 5 kilometers south of the Canadian border. So gives you a good perspective on things. And in perspective in life, for a scientist, is also perspective in science. We could say that what I'm going to be talking about is a little bit of perspective of what you can do in electron microscopy. So to get a little bit more specific, I want to talk about key questions for atomic resolution analytical electron microscopy. That's what we like to do these days, not just look, but also to analyze what do we have in our materials. I want to talk about how modern analytical electron microscopy came along. I want to tell you what we can do at atomic resolution for imaging and chemical analysis. One of the latest things that we can now do is vibrational spectroscopy in the electron microscope, so I'll spend a little bit of time on that. And we can also now do atomic resolution surface imaging using the secondary electron signal. So I want to show you some results from that, and then of course a summary. And for stepping back, a bit of a perspective, the electron microscope is not a new invention. 1931, first images from an electron microscope that had 2 lenses, about 5 power supplies, could magnify the sample 17.4 times. So the images weren't that great, but it was a great, wonderful start. And the second from now World Congress on Microscopy is going to be in Berlin in 2031, celebrating this 100 years of electron microscopy. 9 decades of development, and you have a modern electron microscope. This final form, this is a picture from 2022. We now have something like 70 lenses, 500 power supplies, so we have a lot of deflectors to steer the beam through very accurately. It can resolve atoms with ease. You form an electron probe smaller than 1 atom, about less than the diameter of a hydrogen atom, so that helps getting the good resolution. You can get all kinds of spectra with enough sensitivity to pick a spectroscopic signal from single atoms. And there's enough details in the spectra to be able to determine the atomic type and their bonding. And we can nowadays also hear the sound of just 1 atom by looking at its vibrations. So in this overall perspective, people think that aberration correction was needed to get down to atomic resolution imaging matter. Not true. We knew how to do it back in 1970s with uncorrected electron microscopes. But what you had to do was to go to higher voltage, because that would shrink the electron wavelength and the resolution would get better. So I did a postdoc in Japan in mid-1970s on what was then called the highest atomic resolution electron microscope, HAREM for short. It's operator, the guy who started it, Keinotsuke Kobayashi. He had a great sense of humor, so we enjoyed calling his microscope a harem. And it would produce pictures such as this, where we're looking at germanium in the 110 projection, where you see big tunnels through the structure. And that was a grain boundary here. So we have a 31-degree tilt between this grain, and there's a sigma 9 grain boundary. And at the grain boundary, you can see some dots are bigger than the other ones. Those are 7-fold rings. So you can, based on the structural information you get from the image, you can make a model. You superimpose there where there was a bright dot in the image. You have a 7-fold ring of atoms. In between, you have 5-fold rings. So you're basically reading out the atomic structure from the image. And there's your model. And when you look at the model, you realize that the structure puts itself in such a way that there is not a single dangling bond at the grain boundary. Dangling bonds are very energetically unfavorable. So as this bicrystal grew, it managed to avoid them by doing this fairly complicated arrangement, which is made more complicated by having some twinning planes coming in along the white arrows. So that was pretty powerful. Yeah, that's the 7-fold rings. And we basically could study atomic structure at the 2 angstrom resolution level. But we couldn't tell what kind of atoms we had. If one of those germanium atoms was substituted for silicon, we would have had no idea. And that was a big weakness. So in the 70s and 80s, there was a big push for, can we go from looking at our samples in a kind of black and white way to a more spectroscopic way, where we resolve the color, which will tell us about the structure and the chemistry of what we've got. And the answer was yes, but we need to be detecting analytical signals that go beyond where are the atoms, and that tell us what are the atoms and what are their properties. And so we needed 2 things for this. One, we needed a way to make a small electron probe. And nowadays what you do is you take the brightest source of electrons that we know of, which is cold field emission. You modify the optical properties of the beam with an aberration corrector. So you kind of pre-aberrate the beam so that by the time it goes through the objective lens, the aberrations of the corrector and the objective lens, they cancel each other. and you produce a 1 angstrom or so probe at the sample, which you scan around, and you can scan it, you can stop it, you can analyze, you can image. And the signals that you use, a favorite one is the scattering from the atomic nucleus, which is Rutherford scattering essentially. So the electron goes close to the nucleus, gets scattered to high angles. And another very powerful one is the electron interacts with electrons going around the atom, transfers energy to them, and you have so-called energy loss spectroscopy, and that tells you what kind of atom you had and various other things, band structure around the atom. You can, when an electron beam goes by an atom, the wavefront gets distorted. That results in a modified pattern at the final detector, and that tells you about the phase of the phase changes as the electron wave goes through the sample. So that's a form of holography. And a fourth one is closely related to the first one. If we energy analyze the high angle scattering, that will tell us about what phonon vibrations we set up in the sample. And we've opened that up recently. And then with energy loss, we deposit energy in the sample. The energy likes to come out in de-excitation. It can take the form of secondary electrons, and I'll show you some results from using that signal. It can come out as Auger electrons, which is a little bit more direct, but the signal is weaker. We can come out as X-rays, which tell you very specifically what kind of atoms you had in the sample. And it can also come out as other optical radiation, UV, infrared, optical frequency, and that tells you about optical excitations at the sample. And the whole sum of it is there are many signals, and they are all available simultaneously at atomic resolution if your probe is small enough. And this is what makes electron microscopy extremely powerful. And it's also radiation efficient, radiation damage efficient, in the sense that you do one scan of your sample and all of these signals come out at the same time. You don't need to do a separate exposure for every signal. So STEM, as we know it nowadays, started Albert Crew's lab at the University of Chicago. So Albert Crew was an interesting character, student of Chadwick's. So he knew about accelerators, and he basically came to Chicago to help them with a non-working synchrotron. They had a synchrotron at Argonne National Laboratory that could circulate the protons around, but they didn't know how to extract the protons and make use of them. Albert Crew came along, solved the problem for them. 10 years later, they made him director of the Argonne National Laboratory. He had something like 2,000 people working for him. He was 35 years old. And he said, oh, this is too much administration, not so interesting. I'll go back to university, and I have this great idea. I will start a new type of an electron microscope. Instead of forming a broad beam on the sample and doing imaging with it, I will make a small beam and I will scan it around. So that's where the scanning transmission electron microscope came from. And he built, with his research students and postdocs, the first STEM at the University of Chicago. Here's a picture of the machine. They had all the right elements. They introduced cold field emission electron gun, ultra high vacuum, and they had a Neil spectrometer on there. They were the first group to produce images of single atoms with an electron microscope. But it was uncorrected and worked at 25 keV, so the probe was typically about 3 angstroms in size. So if you look at the typical metal semiconductor, the interatomic distance is less than 3 angstroms, so they could not resolve atoms when they were close packed in a crystal, but when they were spread out, so this is probably heavy atom labeled DNA. They were working on that as an attempt to sequence DNA back then. And they could resolve the atoms as long as they were not too close together. These atoms are about 10 angstroms apart. And they could produce wonderful spectra which would characterize things like adenine, guanine, you name it, all the biological substances tend to have characteristic energy loss spectra. And if you manage to avoid radiation damage, this is very powerful. The STEM has now become the standard electron microscope for material science and physics. And our acronym which dates back from the 60s and 70s, is now also used for science, technology, engineering, mathematics. So I say STEM is a wonderful tool for STEM, and I'll leave it at that. STEM grew up, so Crew put together a microscope which he mainly intended for biologists. He never looked at the material science sample. Mick Brown at University of Cambridge got a STEM and started developing material science applications. And that was the group where I got my PhD from, and they got the STEM exactly the same year as I left to do a postdoc in Japan. So this happened somewhat parallel to what I was pursuing at the beginning of my career, but this lab developed things like Z contrast imaging that suppressed crystallographic contrast that made heavy atoms stand out. So the trick there was just to pick out the high angle scattered electrons, which discriminated the diffraction modified signals, which happen at smaller angles. Tychography, where you used diffraction information at every pixel to improve the image resolution 2 times or more. Cathode-luminescence studies, secondary electron imaging, coincidence studies, where you look at 2 signals in coincidence and you figure out the physical origins of one of the signals because you know what will happen with the other one. And we came along and used the very first microscope that they had, which at that point was 20 years old, split it apart, put an aberration corrector in there, and that was the start of STEM aberration correction. So back in 1997, we had the first successful STEM aberration corrector. Here's an example from Cambridge, not related to aberration correction, but something very powerful, where Nellis, Rodenberg et al. Back in 1995 resolved silicon structure in the 110 projection, 1.3536 angstrom separation between these atoms, done in a microscope that formed a 3 angstrom probe by using the supplementary information in the diffraction pattern. So 1.4 angstrom with a 3 angstrom probe, and that's kind of being used in tychography now. Quite a powerful technique. And also in optical processing. So look at the diffraction pattern pixel by pixel in an image. There is a lot of supplementary information which is very useful. Our proof of principle STEM is now in the Cavendish Museum. So if you're ever in Cambridge, England, go to the Cavendish lab, ask to see the museum. There's wonderful things in there like the apparatus with which J.J. Thomson discovered the electron. There's a model of the double helix, which was also characterized in the Cavendish laboratory. The first radio telescopes came from there. The first mass spectrometer, first bubble chamber, all of these things happen in the same lab. So kind of high honor in that same museum is this corrector which we built with Nicholas Delby between 95 and 97. This is how we went into the microscope. So we took an old VG microscope, split it in the middle, added the corrector, put it back together, and 6 months later we had a working corrector, which was not the world's best microscope, but improved the microscope we put the corrector into. So that was an important step, and we call it proof of principle. We learned how to do aberration correction on that, and our second generation corrector. So the first one demonstrated complete control of parasitic aberrations. That is important. When you do aberration correction, all kinds of parasitic things like threefold astigmatism become very important. You have to fix them in addition to the primary aberration you were curing. If you don't do that, you could end up with a worse image before you started doing aberration correction. So we improved the resolution of the 20-year-old microscope this corrector was built into. And then we turned around and built it into a slightly more modern version of the VG. We got a little bit smarter. We miniaturized scan calls, put them inside the objective lens, put the corrector where the scan calls used to be. So the outside of the microscope didn't change. The only way you can tell there's a corrector inside is this bundle of red cables that brought the power supplies, the currents from something like 35 power supplies that control this optics in here. And that was the work done with Nicholas Delby. And we delivered the first one to IBM Yorktown Heights. So we switched to industrial funding. People would send us an order. One of the, I think number 3, went into a 300 kV VG STEM at Oak Ridge National Lab, and it reliably improved the spatial resolution by about 2 times. So by the time this microscope was built, they got down to 2 angstrom resolution, so improve it 2 times, I used to think at 1 angstrom at 100 kV. We didn't stop there. Now we had a wonderful corrector, but we had a somewhat old microscope, so we said, okay, we have a Ferrari engine that we're putting into a Fiat. We need to improve the rest of the microscope. And we designed this whole microscope here from the ground up. At first, we put it on a VG cold field emission electron gun. Then we designed our own cold fact to it. Here's the first complete microscope that Neon delivered to CNRS, University of Paris in Orsay. So lots of new elements went into it. You have UHV at the sample, very stable sample stage, efficiently coupled deals, and it's been in operation since 2010, and of course we keep on improving it. So in the latest incarnation, we add a monochromator and an EOS to the instrument. So you have a monochromator down here. You have an EOS spectrometer designed for ultra-high energy resolution. You have a flexible sample stage, which in this picture, there's a liquid nitrogen dur. We call the sample to liquid nitrogen. Whatever is shown in the schematic in green goes beyond what Albert Crew did. So there's been some fundamental improvements all around. The objective lens hasn't changed much, symmetric condenser objective, but that's about it. And all of these things together can get you half angstrom diameter probe, so half angstrom spatial resolution, 2.7 milli-electron volts energy resolution. And all the results in the rest of this talk, except for one, were obtained with this microscope. How do we improve the performance relative to what existed before? We have to worry about spatial resolution by forming a very small probe at the sample. And we have to worry about energy resolution, and that's done by forming a very small probe inside the monochromator and in the EOS spectrometer. So it's kind of a related problem. If you want a smaller probe, you have to open up the illumination angles. Aberration correction becomes important. We do it to 5th order at the sample, 5th order at the spectrometer, currently to 3rd order in the monochromator, but we're actually designing a new upgraded monochromator that will do 5th order aberration correction here too. And the optics gets somewhat hairy. We talk about aberration functions, which are basically the wavefront distortions that you have relative to the undistorted wavefront that you want. So if you were an astronomer and you were grinding mirrors, these are the physical shapes that you would have to impart to your mirror in order to fix the aberrations. We, of course, don't do it by grinding. We do it with electromagnets. We don't do it in a single stage. We distort the beam into an elliptical shape. We apply the correction in one direction. We distort it in perpendicular direction. We apply the correction in the perpendicular direction. We make it round again. We fix what's left over. But these are the aberrations we need to worry about. So they all correspond to different shapes. The astigmatisms all have this kind of high modulation azimuthally as you go around. There's different powers for the radius. So this is 2nd order parabola, this is a 4th order parabola, this is a 6th order parabola. So they're all somewhat related, and you can use this one and this one to counteract this one a little bit. And the computer does it all. You teach the computer. A human being would need to adjust something like 30 knobs at the same time, judging whether the image got a little bit sharper or a little bit more fuzzy. That would not be possible. So with our computer, forget it. You would not be able to do it. The results speak for themselves. At 100 kV, working with Phil Batson, going from uncorrected microscopy to corrected one, the double column of silicon that I show you in the ptychography result, not resolvable without correction, becomes nicely resolved. At 300 kV, You can look at silicon in a different orientation where double columns are now just 0.78 angstroms apart. And this is an unprocessed image other than colored. And it came out in 2004, image actually taken in 2003, first sub-angstrom resolution image obtained with an electron microscope. So I think this image, more than anything else, opened people's eyes. Aberration correction works now. We can go below 1 angstrom without aberration correction, even going to 1.5 million volts. We stop at 1 angstrom. We could not go further. So first direct images of sub-angstrom structures in any type of an electron microscope. So once you have that, you look around, what can I use it for? And one of the primary applications stand out to be dropping the operating energy of the electron microscope, which avoids radiation damage in materials like graphene. You drop down to 60 kV, graphene stops damaging by knock-on displacement. Boron nitride, same thing. So the raw image is in gray in the background, and you can see features in there like a very bright atom here, probably sodium. Somewhat bright atom right there, that's oxygen. Boron, there's hardly any image intensity in there, a little bit. Nitrogen is fairly bright. And then you make a model, you refine it with DFT, and the model and the experimental image agree beautifully. So things that you see is that oxygen, that 6 atoms of carbon found their way into boron nitride. And there were other carbon substitutions, and they always happened in pairs. So single carbon atom did not seem to go in, but you could do a 6-fold ring, or you could do carbon pairs substituting for boron-nitrogen pair. Where oxygen sat next to carbon atom, oxygen atom is bigger, so this bond is about 0.2 angstrom longer than the bond next between boron and nitrogen. All of these things you can read out from the image. And it's here at University of Vienna, you have a wonderful group that will do things like put a silicon atom in a graphene foil and move it around with the electron beam. You can do that one. So go on their website, you probably have movies, right? So that's what you can do at 60 kV. The size of the probe at 60 kV is about 1 angstrom. It's smaller than the interatomic distance, so that's sufficient. If we're just pushing for resolution, we still go to somewhat higher voltage. 200 kV, we can resolve 2 atoms 0.57 angstroms apart. So the resolution has improved, and if you look at the images, so has the stability. This jiggle that you have in here, that's because that microscope in Chicago was on the 2nd floor, and there was an elevator down the corridor, and every time things moved, the probe wandered around. So here it should not have been seeing the atom, but either the probe or the atom moved, and you started getting the strong scattering. So these spurious lines over here, that's basically jiggling due to instabilities. And that's been completely eliminated in this image over here. So you have to work on the optics, and you have to work on the stability. And if you want to go further, just like back in Cambridge in the 1995, you use the supplementary information in diffraction patterns. So this is some lovely work from Dave Muller's group at Cornell, not taken in a neo microscope. And here we're looking at a fairly complicated structure in praseodymium scandium oxide. And if you do a line profile through here and here, the praseodymium peak here is about 0.3 of an angstrom wide. So they've pushed the resolution down to about 0.3 of an angstrom using about 0.6 of an angstrom probe. And when you get that far, that's essentially the end of the road for electron microscopy, because atoms oscillate. There's thermal motion and there's 0-point motion. There is no such thing as stationary nuclei in matter. When we look at the beautiful ball and spoke models, they don't capture the whole essence of it, which is that the nuclei are vibrating like crazy at a fairly high frequency, and we're not going to time resolve it in an electron microscope. In fact, Denis Gabor, who did electron microscopy before he did holography, actually he did holography as a method of improving the resolution of electron microscopy images. Back in 1948, in a little book called The Electron Microscope, he wrote, when microscopy gets to 0.5 angstroms, the resolution may have to stop there due to lack of objects. So Mother Nature doesn't give us any objects to test. Resolution of microscopes that can do less than half an angstrom, and Gabor was 100% right. So we pushed it to 0.3 of an angstrom, but it's not going to go anywhere much further. But that doesn't mean that there's no further progress possible in electron microscopes. So where aberration correction and tychography together improve the resolution of microscopes from somewhere around about 2 angstroms down to 0.3. In energy loss spectroscopy, over a corresponding period, we have had 100 times improvement in resolution. So if you look at what Albert Crew did with the spectrometer, they could resolve the native width of the energy distribution coming out from the cold field emission source, about 0.25 of an electron volt, with a very nice monochromator and spectrometer. Back in 2010, Zeiss and Seals together produced 43 milli-electron volts. We are now sitting at 2.7. So 100 times energy resolution improvement, 50 years, 16 times improvement since 2010. Whenever you have 10 times improvement in some measurement in science, typically some new area opens up. And that's what I'm going to be talking about. Where did that last factor of 16 come from? We were very careful about making sure that things did not oscillate independently. Previous monochromators and spectrometers relied on the high voltage being beautifully stabilized. And that can be done up to a certain extent, but pushing much beyond 1 part in a million stability with high voltage electronics gets problematic. So if you have maybe 3 parts in 10 to 7, you can still do. So if you have a 200 kV microscope, you can stabilize it to maybe 50 millivolts. But if you want 3 millivolts energy resolution, you're never going to get it. So you have to find some way of tying things together. You could put the spectrometer and the monochromator on the high voltage, but it gets a little bit impractical. You also slow down the electrons, start repelling each other. You get into a mess with so-called Birch effect. So it's better to keep them at the high energy and find a way to stabilize it. And one way to do it is to put the monochromator on ground potential and have the magnetic prisms in the monochromator that steer the beam around and energy disperse it at the monochromator energy selected slit. Have it tied together with the prism in the spectrometer so that if anything moves, everything moves together. And it's the relative distance between the things that matters. So you can stabilize things very nicely that way. And then you're not tied to the high voltage coming from the electron gun. So what you could have is there's a zero loss peak on this monochromator slit. It could wander off because the energy that you're sending in does not correspond to the energy that the monochromator is selecting. So we get around that by sensing the current falling on the 2 slit halves and putting in a feedback loop that brings the beam back into the center of the slit. When you do the 2 things together, when we first designed it, we thought 30 millivolts should be possible. And we also speculated 10 millivolts may be doable in the future. This slide essentially comes from 2008, when we were still thinking how to do it. So we surprised ourselves a little bit because we're now sitting at 2.7 millivolts resolution. People thought we were a little bit crazy when we said 10 millivolts back in 2008. So what's the new thing that this allows us to see? Previously, our energy loss spectra were dominated by the energy distribution of the source. And it was very wide. You monochromate, this region becomes accessible. Whatever signals are in there, you can see it. And that's, of course, where the phonons are. So take hydrogen oscillating against oxygen in a water molecule. The energy is about 450 millivolts, somewhere out here. Take carbon and oxygen double bond in a biological molecule. The energy is about 200 millivolts. None of that was visible. Now it is. So that we say that the signal was hidden in plain sight, and we need to work a little bit harder to dig it out. So now we have access to phonon scattering, And it's important to realize that there's actually two types of phonon scattering. There's what we call the dipole signal, which is highly delocalized, and it basically, best way to think about it is that there's a virtual photon which is exchanged between the fast electron and the sample. The sample has to have electric dipole moments, and it's the way light interacts with matter. Okay, so we can see that signal, and we can see it without sending the electron beam through the sample. We can have some distance of the order of 30 nanometers, 100 nanometers, still interacts very nicely. There's a delocalization at the kind of energy exchange. It really comes back down to delta E, delta T has to be greater than h bar. So uncertainty principle, and we can probe the sample without irradiating it, which is wonderful for minimizing radiation damage. It does cost you resolution. We will not get atomic resolution with that kind of a signal. But we also have a second type of a signal, which we call impact scattering, following people like Ebach with low energy EOS. And that one comes from the electron interacting with the nucleus much more closely and being scattered to a high angle. So this one we can select by just putting an aperture in the diffraction plane and saying the only electrons we want are the ones scattered to high angles. This one we can select by not putting the beam inside the material. So we can switch from one type to the other, and when we do that, we can start exploring phonon spectroscopy. So back in 2014, we published a paper in Nature called Vibrational Spectroscopy in the Electron Microscope, and that basically opened up a new field. At the same time, similar work was done in Japan, but the spectrometer that the Japanese had would only give them about 50 millivolts. So they were very good picking out the sample where there was a vibrational signal they could detect at 400 millivolts. We looked at a whole bunch of materials: boronite, SiO2, silicon carbide, titanium hydride, epoxy resin. Everything vibrates. If you can resolve the vibrations, you will see it. And the applications that came soon after. So the first one, we were very interested in looking at biological things without radiation damage. And it's a proof of principle. Take a crystal of guanine. It's a platelet of guanine extracted from a fish scale. And put the beam just outside, and we have enough control of the beam so that if the maximum of the beam is sitting 30 nanometers away, that's essentially zero flux going through here. When you do that, there's essentially no radiation damage, but vibrational spectra can be seen. This is collaboration with Peter S. at Arizona State University, and the sample came from the Weizmann Institute in Israel. And here are the spectra. And there's also illustration of evolution. So this kind of spectroscopy, optical spectroscopy, closely corresponds to the infrared. So here's an FTIR spectrum. And you can see that with the original spectrum we got in red, there's some reasonable correspondence for the hydrogen peaks. So the high energies, you have to have something light which will oscillate at high frequency. And these four peaks, B, C, D, E, they all have to do with the hydrogen. Carbon-hydrogen stretch, nitrogen-hydrogen, symmetric NH2, asymmetric NH2. So not only are you detecting hydrogen, you're actually seeing how it is bonded. And the strongest peak, that comes from this oxygen atom sitting next to carbon, double bond, very sharp resonance. So you get that's a very characteristic peak that shows up in a lot of biological molecules whenever you have this kind of a bond. So the first spectrum that we got looked like this. Nowadays, we improve the spectrometer, we get much richer spectra, and this is actually now about 3 years old, so we can probably do better still. And interestingly enough, we can go to energy regions where optical spectroscopy doesn't reach. So transmission through lenses, you stop at 0.1 eV, that's about 100 wave numbers, inverse wave numbers. Electron microscopy can just keep on going. There's no problem about transmission through glass. It's quite powerful. That beautiful sharp peak exists in this molecule, which comes from L-alanine. And if you change this carbon atom here, swap 12 carbon for 13 carbon, the peak shifts by 4.6 millivolts. 4.8 millivolts. And these are, by the way, experimental spectra. So we've gotten a little bit better in how to work on spectra to get rid of the noise. So in principle, this biological molecule behaves exactly the same way, whether it's carbon-12, carbon-13. Biological functions are unchanged, so you can feed this kind of L-alanine. It's one of the 20 essential amino acids for life. You can feed it to some rat, find out where it went, use it as a tracer. Should be quite powerful in biology. I haven't seen it applied yet. We need to talk to more biologists that we can do this for them. So isotopic substitution could be used to study metabolic pathways in cells and whole organisms. Another interesting experiment, take heavy water, D2O, prepare biological samples in the way they do for frozen hydrated microscopy, measure how much regular hydrogen you had and how much D2 you had. So we're actually measuring just the hydrogen-oxygen vibration bond. So if you have a mixed molecule, you still see two separate peaks in here. It's either the deuterium-oxygen stretch or the hydrogen-oxygen stretch. And it turns out that you hardly got any deuterium, but if you swap the medium which provides the water vapor during the preparation process, this one was still done with regular water. The sample had D2O in it, but the medium providing the moisture had regular water. If you swap the vapor in the vitrobot, you end up with a spectrum like this, where the D2O signal is much enhanced, which is basically telling you the water that you have in the sample did not come from the sample itself, it came from the vapor phase that the sample was prepared in. An interesting thing, biologists kind of love this sensitivity. So we were trying to figure out the radiation damage pathways. There's hydrogen bubbles that form in the sample. Did the hydrogen come from the protein in the sample or from the water? So we had regular proteins and heavy water for the embedding medium. That turned out to be too tricky a problem. The bubbles came and went at liquid nitrogen temperature, not stable enough, small signal relative to the background, but this was an interesting result that came out of that. Okay, now back to material science. So we're giving up this idea that we can decrease the spatial resolution and avoid radiation damage. With material science samples, they're much more sturdy. So you can do things like send an electron beam through the material and look at the diffraction pattern and select a particular line in the diffraction pattern, form a two-dimensional pattern in which you'll be looking at different momentum exchanges. So you can relate it to the Brouillard zone diagram with points like K, M prime, K prime, gamma point. There's an X point somewhere around about here. And if we do a line profile like that, we get a two-dimensional pattern on the detector of the yields. Takes something like 16 minutes, but this is following some work in Japan where they did it serially, and it took something like 3 days to get this kind of data. So in 3 minutes, we get this omega Q diagram, as we call it, which tells us about phonon dispersion. And it changes quite heavily between room temperature and a heated sample. One of the big changes is that you can start looking at energy gain, symmetric with energy losses. And there's some interesting changes in here, like the K and K prime data in the experimental spectra. The data is not the same. There's important changes. Even though it should be symmetric, turns out the theorists don't actually have the right model. So for once, the experimentalists are ahead of the theory, and theory is going to have to catch up. So temperature dependence of phonons can be explored very efficiently, and we still keep something like 3 nanometer spatial resolution on the sample. So when we have good momentum resolution, we have to give up spatial resolution, uncertainty principle. You can't have infinite spatial and momentum resolution at the same time. But to get this kind of angular momentum resolution, 3 nanometer sample probe on the sample will do it. So we still have spatial resolution. We can probe defects like this. And here's looking at a particular defect in a stacking fault in silicon carbide. 3C silicon carbide. and we want a good spatial resolution. So the first step is we don't look at the gamma point, which is the forward scattering. We look at the X point. So this is work done at University of California, Irvine by Xing-Shu Yan. If you look at the X point and you look at the stacking fault of the book silicon carbide signal, the spectra look very different. And then you say, okay, now I can map it. So here's the image. There's a stacking fault in here. And then one-dimensional scan in here, energy this way positioned along the sample for this particular signal, and you can see how it changes quite heavily at the defect. And interestingly enough, it's not 100% symmetric. So there's stronger depletion on the right side. This LA vibration band comes in a little bit more strongly close to the stacking fault, and the transfer acoustic phonon is very much enhanced, and the energy changes a little bit at the stacking fault. So for the first time, there's no other technique that we know of. We can look at vibrations at individual defects, individual structural features in materials. Optical spectroscopy would not get us anywhere the resolution that we need. With electron microscopy, we don't have atomic resolution for this kind of selection, but we have a couple of nanometers spatial resolution, and that's quite interesting. Now, if we give up on the idea of having good angular resolution and angle integrate a bit more, we can keep the atomic resolution. And here's a beautiful result from the SuperStem lab, Quentin Ramas, Frederick Hage, at Desbury National Laboratory in the UK. You select the high angle signal, so we basically deflect the bright field, the unscattered electrons, so they miss the selection aperture going into the eels. We have a silicon atom in graphene, and we move the probe from some distance away to probe these different atomic positions. So here's the silicon atom, here's the nearest neighbor, second nearest neighbor, third, etc. Here's the experimental results. The fourth nearest neighbor, it looks essentially like bull graphene. By the time we're at the first nearest neighbor, the spectrum starts looking a little bit different. On silicon, it's now very different. Here's the simulations, corresponds very nicely. So not unexpected, the vibration energy shifts to lower values because we have a heavier atom. It goes basically as the frequency goes as 1 over the square root of the atomic mass. And the fine structure in here at the higher energies, that changes quite a bit as well. So if you want to be poetic about it, the electron microscopes can now hear the song of one single atom. And when we went into this, we had no idea that we would be able to do something like this. So much for vibrational spectroscopy. I want to spend a little bit of time talking about what we can do for the surface signal, which we image with secondary electrons. It has been done before in a 200 kV microscope. We bring the advantages of being able to produce a 1 angstrom beam at 60 or even 30 kV. We have clean vacuum, ultra high vacuum. That's important to be able to probe the surfaces rather to look at contamination. And if we bring in the sample dirty, we can clean it with the lasers that we bring in. We actually, no big hurry. This was not too much competition. We started the project 5 years ago, and finally this year we have the whole apparatus together, and we're producing nice pictures. So to go back to what was done back in 2009, yttrium barium copper oxide, IPCO, high temperature superconductor. You look at it with there's a secondary electron image, there's a high angle dark field image. The secondary electron image, the resolution goes up to 1.4 angstroms very weakly, and you have to do a lot of averaging to get a signal like this. If you try to look at something, a moly disulfide, you don't see anything because it tends to contaminate. Here's our detector, just proving that it works. So we have high angle dark field image, SE image, looks a little bit worse resolution, a little bit more noisy. Same thing for single atoms, but whatever was a single atom of gold detected in the high angle dark field signal shows up in this SE signal as well. You have to worry, could it be backscattered electrons? They could potentially produce electrons by rescattering of the right energy. So you flip the foil with gold particles over and you look at the image. high-angle dark field looks right through the foil. In SE signal, nothing shows up. And that's 20 nanometers of carbon stops the signal. So if it was backscattering from the gold atom, then reflecting from the walls of the microscope, that would not be happening. So here's looking at graphene with a nitrogen and boron substitution. So the nitrogen atom shows up bright. The boron atom here shows up as dark. In the SE signal, they stand out even more strongly. The contrast levels are not fantastic. This is the absolute scale, so 0.42 going up to 0.43, about 2% change in the signal. But the signal is there, and this is not average other than smooth. So we're resolving things with the atomic resolution, and we can tell that we have the image there. We can correlate it with the yields. So nowadays, with energy loss spectroscopy, you can do mapping, and the map tells you, oh, that was a nitrogen atom here, that was a boron atom here. And you can also do the total energy deposition map, which is basically multiplying the EO signal intensity by the energy, and you find a very close correspondence between this image here and this image there. And that's because the SE image really comes from the energy being dumped into the material and coming out in the form of the SEs. But that works 100% on a monolar thick sample. If you have a bulk sample, it changes quite a bit. So the SE image, you cannot get it by this kind of consideration. So SE signal is similar, but subtly different from the total deposit energy map. And here's my last slide of experimental results. Molybdenum disulfide. It has a vanadium substitution right here. That's the yellow arrow. These bluish arrows, sulfur vacancies. So it's easy to dissolve sulfur. And you can see, so you basically just follow the line of perfect. So that's a sulfur atom, that's a sulfur atom, actually double sulfur atom. Here it is missing. So you can see that in a high-angle dark field. In the SE image, shows up as big holes. You can do things like differential phase contrast, shows up in here. You can do bright field, nothing shows. So you have different signals and you use them for different things. So the vanadium substitution, again, in the bright field image doesn't show up very well. DPC is right there, but not as strongly. In SE image, you can see it very clearly. So the more signals you have, the better you are prepared for a wide variety of samples and material science phenomena. And that's kind of the way the world is going. And here we have divergence of film. That's another really useful signal. So that's kind of the story of modern microscopy. Do the optics as best as you can, and then use the computers and different detectors to push you as far as you can go. So my conclusions, electron microscopy has seen a lot of progress since 2000. So we're now in a new century since 23 years ago, and much of it was driven by aberration correction, ultra-high energy resolution yields, and also the computer extra power that you get through smart software. We have better electron detectors, we have more stable sample stages, and we have wonderful software that can analyze things and improve the image quality and combine signals in ways that give us completely new information. And many people have contributed, so what I showed was mostly electron microscopes produced by Neon, but the practical applications, that came from like 10 different labs in the world. You can't have a group of 3 people pushing the field like this. You need the international collaboration, and we greatly appreciative of people helping. So 3 of them are sitting here in the audience, and it's kind of a wonderful international effort. And I hope it very much continues. There's still a lot to be done. And I thank you for your attention.